that we're going to work with today on these USB drives. Just copy both of them to your computer. One is called, I think, Orlando. The second one is Practice 2. Anyone needs a pen? Oh, you know what? For now, we don't need it. That's the URL.
Okay, great.
So. Yeah, perfect. One's called Orlando, the other one is Practice. Just copy them to your computer. Yeah. But you don't need to write for now. Nothing.
So here's a shorter version I made. So AF7QJY.
A bit shorter. Thank you.
Yeah.
Those are the same as what's on the
Yeah,
card.
exactly.
Yeah, that's
Cool. Thank you.
We'll just wait. Like
yeah,
few
of course they're
minutes.
coming in.
Just enough.
Oh, okay.
Start SPSS on the computer. And you have two data sets on this USB drive. One is called Orlando, the other one is Practice. Just go. You just have SPSS. And you don't need to just for practice. You have two data sets on this USB. One is Orlando, the other one is Practice. Just copy them to your computer. Oh, that's fine. Yeah. Yeah, sure. I'm gonna pass a USB drive.
You said there's a folder named Orlando.
It's not a folder. It's two files. One Orlando, the other one is
Oh.
Practice 2. Excellent. So let's start. Just go and tell me your name. I'll try to remember it as best as I can. Starting with you,
My name is Cleon.
Cleo.
Cleon, yeah. It's like
Okay.
Leon.
Perfect. And your program? Like how did you
I'm
get?
communication informatics.
Perfect. Cleo.
My name is Thibaut.
Thibaut. Okay.
I'm from communication informatics.
Nice.
Hi, I'm Amber. I'm a DSM student taking audience analysis.
With
Dr. B.
okay. Nice.
My name is Anna. I'm also in DSM and I'm also taking audience analysis at Dr.
Okay.
Sergio, Public Diplomacy Program.
Nice.
Hi, I'm Sylvia, and I'm a first-year student in public relations, graduate student in public relations.
And they make you do this. Why? Excellent.
Christy, fourth year Ph.D. student comm.
Sydney, second year public diplomacy master's student.
I'm Kristen, same as her, second year diplomacy student.
And
I'm Chen, second year communication management student.
okay, perfect. And you're also taking a class,
Yeah,
audience analysis.
analysis.
Nice. Okay, so I'm Nathan. I'm from the PhD program, like Christy, and most of my research is somehow related either to health communication. So we're working on how to make messages more effective, more persuasive, or to media psychology, where we're looking at what are the underlying mechanisms that people go through when they are exposed to media. And I'm just sharing this information with you because the type of examples that I'm going to use, the type of data sets that we're going to use are from this content world. So just warning you. SPSS, why do we need it? It's been around for almost 50 years. Very reliable. It was designed for the social sciences. Recent versions put much more emphasis on health sciences. We can see it by the type of analysis that they include, the type of things that they change in the software. Very common in the industry. So if you're in the academia, there are many alternatives. We have SAS, we have R. There's a gradual movement from SPSS to other softwares that are somewhat more open source softwares where you can code. However, in the industry, SPSS is by far the most common analysis tool. I'm just going to give you an example. Last week, got an email from someone who is looking to recruit people for their company, and I highlighted that what they really want is someone who knows SPSS. Really nice job, by the way, if you're into relocating to London. So let's start the way that I see this workshop, and it's also, I'm gonna try to get your feedback during the workshop. So I'm gonna start at a very, I would say, low level, and we'll try to cover as much as we can. So we have today and we have next week to cover quite a lot of interesting and relevant material. It's going to be a lot of hands-on workshop. You're going to do it. I'm not going to get into a lot of the statistical, theoretical, equation stuff. With that said, it doesn't make sense to talk about significance, proportions, means, modes, t-tests if you don't know what it means. So please stop me. If something is not clear, we'll stop. We'll talk about it for 2 minutes and hopefully it will become clearer. SPSS. Do you have like in general, do you have some experience with SPSS? Like just shout.
No.
In terms of no,
Zero.
nothing. Okay,
Nothing at all.
excellent. So SPSS works with several types of files. Three relevant files are the data file, the one that ends in .sav. That's the data file. That's the file that includes all the data, the file that we're going to work with most. Another type of file is the output file. So every type of analysis, everything that we're going to do in the data file is going to come out in the output. That's the results. We want to know if there's a significant difference between the groups. We want to know if there's a correlation. We want to know what the mean is. We're going to look at the output file. The last type of file, we're not going to really work with it today. I just want you to be aware of it, called the syntax. Syntax is basically the language of SPSS. So everything that you can do in the software, all these windows, all these options, you can also code in the syntax file. Why do we need the syntax file? Many reasons. Let me just emphasize two reasons. If you're working on a large project, especially those projects where you started today, the project will end in 17 years, you're probably not going to remember what you did. So syntax is a really nice diary, a statistical diary where you can always go back and see what you did or what other people did. Because sometimes you're collaborating with different people, some of them move on to different projects, and you want to have some knowledge of what happened, how the variables were computed, and so forth. The second reason is that if you're working on a relatively big project, you're going to do the same procedures all over again, all the time. So you're going to check reliability for this scale, and then you're going to move to a second scale, third scale. You're going to do it 17 times. It's going to be much faster to do it through the syntax window, because you're just running the same command again and again and again, only changing the name of the variable rather than finding the variable in the data view and choosing, clicking the right windows and so forth. So we have three files: data, output, syntax. Now let's look at the SPSS. We have two types of windows, or two types of view. One is the data view and the other one is the variable view. And you can move around. Essentially, the variable view is the place where you define the variables. The data view is the place where you put all the information about your sample. An easy way to understand it would be, so I gave you this mock questionnaire. So an easy way to understand it would be that variable view, these are the questions, and the data view, those are the answers. Okay, so if we start, let's see just what are the types of things that we can define in SPSS, and you can do it with me. So I'm looking at my questionnaire. Look at your questionnaire or the type of answers that you want to input. So the first variable we need to give it a name. Let's say, how old are you? That's probably going to be age. The only thing to keep in mind that when we give it the name, we can't have spaces in the name, and it should start with a letter, not with a number. The second option, type, is essentially the type of variable that we're going to use. The two types that we commonly gonna use are either numeric, which is basically a number, so we're gonna use a number, or string. String, if that's what we want to write a name. For example, place of birth, it's not going to be a number. It's going to be a name. Okay, Los Angeles, for example. So we're going to use string for those cases. In the case of age, that's a number. So the next option is the width, is basically the number of characters that we want SPSS to give us. It's not going to really affect our variable so much. Just means that, I'll show you later, but it just means that in the data view, it's going to allow us more or less characters. Decimals is the number of numbers that we want to see after the decimal point. Usually it's 2. That would be the default. The label, so I told you that we have the name, but we are somewhat restricted, so we need it to be short. We can have spaces, we can start with a number. With label we can do whatever we want. So for example, we can write the whole question, right? How old are you? Because we want to remember how we actually asked it. Values, this is less relevant for age, but yeah, we're not going to touch values right now. We're going to do it with one of the other variables. Missing is basically SPSS asks you what happens if someone didn't answer, or if someone gave an answer but it doesn't make sense. For example, in the age someone wrote 900. How do you want to treat it? So the convention would be to define values for the system missing. Usually we use 999, that's the convention, and we can even use several different numbers like 999, 998, and then when we code the data, we remember that every time that someone didn't answer, we're going to write in age 999. Every time that someone didn't answer, or every time that someone gave just a wrong number, but it's still a number, we're going to write 998 if for some reason we want to differentiate between those. The practical implication of this is that any analysis that we're going to do, SPSS will know that, okay, so these are not real numbers, these are system missing. Just imagine that we are not defining system missing, we have 999, and we're running, we want to know what the mean of the distribution is. So we have a person who's 900 years old. So it's gonna, right, push the mean upwards. So we have to let SPSS know that we are actually dealing with a missing value. Columns is very similar to width, just width focuses on the number of characters. Columns is essentially the width of the column. So we can make it larger and hopefully, yeah, you see it becomes wider here. We don't really need to touch this ever. Alignment for some reason. This is the measure is quite important, and that's the last important thing in this window. For those of you who have some background in statistics or in research method, we're generally differentiating between 4 types of variables based on their measurement scale. How many of you have some idea of what I'm talking about right now? Okay. So variables can be nominal, like gender and race, where we're basically, the only difference between the categories is I can say males are not like females. That's why we call it nominal. It's like names. The only difference is the names, but we can't really order them, right? We can't say males are more than females. We can't divide males by females. We can say the more male you are, you're either male or not. You're either born in LA or not. You're either a graduate student or you're not. This is your ID number or it's not your number. Yes, no. The second type is the ordinal type. So here, there's a difference between the names, but also there's a meaning to the order. For example, like Kert scales, if you're familiar with this type of scale, where we're asking you, how happy are you? And that's from very happy to unhappy. Okay, so if you're happy, you're happier than someone who is not happy. But you can't really, like the intervals are probably not the same. Think about another example, a running contest. So we have a person who came first place, second place, third place. I know that the person who came to second place came faster than the person who made it to third place. What are the intervals? I don't know. Maybe first place and second place, there's like a half second between them, and then 20 minutes between second place and third place. So ordinal is when the order is important, but the intervals are not the same. And we have it a lot in the social sciences, especially like Kert scales, right? To what extent we want to measure shyness, so you have a lot of items that relate to shyness. When I'm at parties, I tend to be quiet, from completely agree to completely disagree. This is all falls under ordinal scale. Then we have interval, which is the least important one of them. Just, I'm going to briefly tell you what it means. Just forget about it. We're not going to work with it ever. Interval is where we have the categories are different, like with the nominal. The order matters, and they have the same interval. But their zero is not what we call an absolute zero. So for example, if we measuring IQ and someone gets a 0, it doesn't mean that they don't have IQ. Okay? If we're talking about typographical height and we're at level 0, it's not as if there's no height. The numbers are arbitrary. That's interval. We don't have good examples for that in social science except IQ, typographical height, temperature. So we're not really using it. Every time that we have interval, we're actually using ratio. Ratio is everything that has to do with numbers. Okay? If someone weighs 0, they don't have weight. If someone has $0 in their checking account, they don't have money in their checking account. If someone likes 0 songs by Justin Bieber, they don't like songs by Justin Bieber. Okay? 0 means nothing. So that's the 4 scales that we're using, or the 4 levels of measurement that we're working with in statistics. That's a really brief introduction to this. So we need to determine whether age is a scale, which is a ratio, ordinal, or nominal. What do you think? Age is scale. Excellent. If you're 0 years old, you don't have an age. The last one is, honestly, that's something that they added recently. It's not really important. They are asking you, what role is this variable going to play in your analysis? Is it going to be an independent variable? Is it going to be an outcome? Is it going to be a variable that's going to help you to divide your sample into subsamples? So input is an independent variable, something that affects something. Your education affects your salary. Education would be an independent variable, an input. Salary would be a target. Honestly, it's not really important. Usually I don't touch it at all. It would become important if you have a very long data set and you just want to make sense of it. You want to remember, okay, so I wanted to check this as a predictor, so I'm going to put it on input. Also, it's important to note that the 90% of these definitions, it's mostly for you. So if you're running an analysis that's, you can only run it with 2 variables that are ratio, but you're actually using variables that are defined as nominal, SPSS would do it. The analysis won't make any sense, but SPSS would do it. So most of these definitions are mainly for you. Just to remember, okay, so that's how I measured it. Let's do another one really quickly. Let's do the religious affiliation one, just because it's obviously nominal. Okay, I'm Hindu, it just means that I'm not Christian. Doesn't mean that Hindu is more or less. I can't divide Hindu by Christian. I can't be 0 Hindu. So we can call it any way we want. Again, it's numeric, and I'll show you why. It's numbers. I'll show you in a second why. And which of the following, etc., etc. Now, values. So that's the questionnaire, and we're going to lose it, we're going to forget about it. Obviously, in the analysis, SPSS doesn't know about the questionnaire. What we need to do is that we need to input the answers. So 1 would be, for example, 1, label, Catholic. Oh. 2, Protestant, and let's say, and let's say 4, Jewish. Giving a shout out to my people. Oh, I just erased the Protestant. Add. So basically we need to add all of them. Missing, it's the same thing. And in terms of measurement, this time we're talking about a nominal scale. Really quickly, let's do political ideology, just because it's an ordinal scale, right? So if you're 3, it means that you're more progressive than someone who is 1. But we don't really know. It's so subjective. What is the difference between 2 and 3? Is it the same as the difference between 5 and 6? If you're 0, does it mean that you don't have political ideology? No. So, we have on a scale from and yada yada yada. And here we can, what I like to do is just to include the opposing poles. So 1 is conservative, because I'm going to forget how did I define it. And 7 is progressive. Okay. Missing is the same thing. You can actually copy and paste. And that's an ordinal variable. Any questions? Excellent. So now that would be like the back end of our data, the questions. Now look at the answers. We're moving to data view, and now we have our questionnaires. Someone is 33. Their religious affiliation is Catholic, so it's 1. Remember, Catholic was 1. And their ideology is that they're very progressive. We have another person who is 55. Their religion is they're Jewish, and they are highly conservative, or on the midpoint of the scale. You get the idea? Now, if you're working with a survey software, like we usually do at USC, like Qualtrics, then you can get the file ready from Qualtrics. But just, it will be a bit raw, in the sense that you'll have to go and you'll have to define the missing values. Because if you won't define the missing values, you're going to ask for an average age and get 200. Hey, how come I got 200? Because you didn't define 999 as a missing value. So we have 2 people who are 1,000 years old in your sample. Any questions? Okay, easy, right? It's a very easy software. Very easy. Okay, we're moving on to what? Okay, excellent. Let's talk about descriptive statistics. So that's the basic of how to input data into SPSS. Let's talk about descriptive statistics, which is a branch of statistics that focuses on how to describe the sample. We have a sample. We sample it from some type of population. It can be USC students. The population can be NGOs. The population can be actors. And we have that sample, and we needed a way to describe it. So the first way would be with a central tendency measurement. And we have 3 of those. Mean, that's the average. Okay? Median and mode. Is that familiar? Okay, so mode is the most common one, but it has some problems, right? For example, what about this distribution? The mode here is 2, but it doesn't really describe the distribution. So we have another way to describe it, which would be
Medium or it doesn't work. Maybe we should use standard deviation.
Nice. So we have a median or a mean. Median just tells us what's the value at the center of our distribution. But again, what about like here, the the median would be 2, right? But it doesn't describe this 100. So we have the mean, but the mean obviously is highly affected by outliers. So if we had Mark Zuckerberg here and we would compare our annual income, he would be an outlier that would affect our mean. Okay, or if you our how much we pay in our taxes, and we had our President Trump here, it would affect it to the opposite direction, right? And I'm just frustrated with the text. Okay, so central tendency gives us some of the picture, not all the picture, especially when we think about this example where the mode, the mean, and the median for both of these distributions, if you think about it, is 3, but the distributions are different. So we need what we would call measures of dispersion. And we have few of those. Range, which is basically the maximum unit minus the minimum. Okay, so here it would be 2. The problem with the range is that it's affected by outliers again, because we're looking only, in a sense, we're looking only at the outliers. So one way to deal with it is to look at the interquartile range, which is basically the center 50% of the distribution. We're dividing our distribution into 4 quartiles and looking only at the center 2, quartile 2 and quartile 3. So we're removing the outliers by definition, but we're removing a lot of information. We're removing 50% of our distribution. That's crazy. We don't want to do it, especially if we paid those people. So we have 2 better options. One of them is variance, which is a very simple concept. Often students have some issues understanding it, but if you think about it, it's very simple. It's essentially what we're measuring. Let's say that that's our average, so that would be, for example, education. That would be income, I wish, right? The more educated you are, the higher your income is. It's a nice linear relationship. Let's say that that's the average. But people are not on the average, right? Actually, people are, and they'll have some outliers. And some people are on the average. So the variance is essentially all those distances from the mean. Why do we need to square them? Because if that's the mean, and these are the distances from the mean, then by definition, you have the same distance above the mean as below the mean. If we're just going to add them up, we're by definition going to get always 0. This going to cancel this all the time. So we need to square them. That's the variance. The problem when you square them, you get a very large number. We don't want to work with large number. So we're doing the square root, and that's our standard deviation. Okay, so every time from now on, where you need to describe your sample and you want to provide some information about the distribution, you should always have a nice combination of central measurement tendencies, that's your mean, mode, median, and some type of dispersion measurement. Usually the best thing is mean and standard deviation. And I'll explain in a few minutes why, how much information we get just by knowing these two numbers. We get a lot of information. We can actually, to some extent, visualize the whole distribution just if we know these two numbers, the mean and the standard deviation. Any questions? Don't worry about calculating the stuff where SPSS is going to do all the work for us. Okay, just going back to my previous point, sometimes you can have different distributions, but same dispersion, same standard deviation, see, for different distributions. So you need to combine central tendency measurements with dispersion measurements. How to do it in SPSS? Very easy. So if you can just load the Orlando file. Few words on this file because we're going to work on it for most of today. So almost a year ago, if I'm not mistaken, in June 2016, there was a shooting at a nightclub in Orlando, and we were interested at how the shooting was framed. So certain media outlets framed it as Islamic terror, mostly right-winged outlets. Other outlets framed it as a hate crime because all the people who were killed were from the LGBTQ community. And the person who did it, you can interpret this both ways. So the question that we asked were, what are the implications of these frames? So we had two conditions. One where we emphasized, gave more salience to the Islamic nature of the events. The other where we gave more emphasis to the hate crime nature of the events just by manipulating the headline. And we measured a lot of outcomes that we're going to play around with in the next hour. So, okay, so you have the Orlando file? Excellent. What? It's still loading?
Well, I just don't know how to open it.
Oh, you just click on it twice. Or you can load it from the SPSS if you just go to File, Open Data. Sometimes it takes time. Okay, so we'll start very, very slowly. So, as you remember, we have the variables here already defined. So if we want to go, for example, and see how gender was coded, we can see that gender 0 is female, 1 is male. If we want to see how the extent that respondents were familiar with the attack was coded, so we can see that 1 was entirely unfamiliar and 7 was entirely familiar. And we have two conditions. So we have 0 is the condition where it was framed as a terror attack. 1 is a condition where it was framed as a hate crime. And if we go to data view, we'll see basically the answers. If we scroll down, we can see how many respondents we have. That's our sample, 243. So to get the frequencies or the central tendency measurements along with the dispersion measurements, we go into Analyze, Descriptive Statistics, and you have the steps here.
and frequencies. Now you need to choose the variables that you want to work with. So as you can see, this window gives you the labels that tend to be long. So if you right click, and I don't know what it means for you Apple people, you can display variable names, which is usually somewhat more convenient to work with. So let's work with age, let's work with ideology. And an interesting question that we ask them about their social network. So we ask them, with how many people do you discuss issues related to current events with? And then for each person that they named, it was from 0 to 10, we ask them about their gender identity. We basically wanted to know with how many non-cisgender or LGBTQ people they talk with. And the assumption there that for people who know a lot of LGBTQ people, the effects are going to be weaker. No matter what, you're going to think that it's targeted the LGBTQ community. That was one of the hypotheses. So we have 3 variables here, but we still didn't told SPSS what the information that we want to get. So we go into statistics, and now we're going to choose means, medians, modes. We can choose sum. No one really wants to know the sum usually. Standard deviations, variance, range. Let's go also with minimum, maximum. And let's go with quartiles. Quartiles is for the interquartile range. And yes?
Sorry, how do you get to the frequencies window?
So you go to Analyze, Descriptive Statistics, and then Frequencies.
Okay.
You move these variables to this window, and then click on Statistics. And also you can ask for a specific percentile. Let's say I want to know what is the age, what is the political ideology, and what is the network composition. How many LGBTQ people you know, basically, for people who are at the 99th percentile for each of those distributions, and also for, like, I don't know why, for 35th percentile. Sometimes we want to know specific percentiles. Continue. Now we have also an option to display it as either bar charts, pie charts, or histograms. Usually, like, the common thing to do would be use histograms for ratio variables, and we'll see why. Just because it presents it in a somewhat better. Bar charts work better for ordinal data, and pie charts work better for nominal data, because if you have too many slices in your pie, it looks like some painting from the psychedelic era. I'll show you maybe later. Just looks weird. So let's go with a histogram, just because we have age here, and we don't need to come more crazy than it is. Oh, and if you go back to charts, I also want you to click on a normal curve on a histogram. Okay, so if you click here OK, you're gonna get an output window . So let's just read the output. Did you all get an output? Okay, just click OK when you're done. So we have 243 valid responses. Valid. means that none of them were identified as missing. For age and for political ideology. However, check this. We have 15 missing responses for network composition. And I don't know why. Maybe people just, I don't know, that's like too personal question. I don't want to answer it. Or people had a hard time figuring it how they going to answer it. So they just didn't answer it. In terms of mean, the average age was 40.6. Political ideology was in the middle, 4.3. Remember, the scale is from 1 to 7. And network composition was 0.9. So on average, our respondents talked to less than one LGBTQ person about current affairs. In terms of median, everything makes sense. Also mode. But you see how different it is, right? We have our standard deviation for each variable and our variance. Again, if you're writing a paper, if you're presenting a report to your employer or to a customer, usually what you want to focus on is, well, if it's the industry, you want to focus on what makes you look better, but usually it's a mean and standard deviation. And if you remember, so we ask for quartiles, that's the 25th, the 50th quartile, and we also ask for these percentiles, 35 and 99. So the person who is on the 99th percentile for age was was on average 79 years old. And here we get the whole distribution, first for age, then for political ideology, and we can see that we had 5 people who were 19. They are 2.1% of the distribution. And we also get a cumulative percent, so that's 19 and below. We had one person who was 84 years old, and he is or she is 0.4 of the whole distribution. We had 45 people who identify themselves as progressives, and it's 18.5% of the distribution. And we had 2 people who were talking with 9 LGBTQ people on a daily basis, and they are only 0.8 of the distribution. Interestingly, remember that we had some system missing, so it means that we always need to look at the valid percent, because it basically subtracts the missing values. So it's actually 0.9. There are more because we had few missing values. Any questions? And now the distribution, we're going to talk about distributions in a minute, but just see how it looks. It gives you the normal curve on each distribution. That's a very skewed distribution, and we're going to also see how to measure skewness. But we would expect this type of distribution for this variable. We have few people who know a lot. Many people don't know any non-cisgender individuals. Any questions? Right? It's really easy. Right? SPSS is really easy. It's nice. It does all the hard things for us. So here we have the steps and the results. Another thing that I wanted to show you, sometimes we would want to split our file, our data, based on some variable. because it's nice, it's easier to present information in that way, or for some other reason you want to know if there are some differences between different groups in our sample. So to do this, you would go to Data, Split File, and choose the variable that you want to split the file by this variable. Let's do gender, and we can either compare groups, so our output would compare males, females, or we can organize output by groups, meaning that it's going to be males first or females first, whatever we coded as 0. Females first, males second. Okay, so we have gender here, and we're going to click OK. And now we're going to run the same thing again, analyze descriptive statistics, frequencies. We have all the options here already selected. We're just going to click OK. But now our output is going to be split. We're going to have output for all gender, then for females, then for males. And we can eyeball some differences, right? So we see that on average, males were older than females. On average, females were slightly more progressive. And on average, females knew or reported on talking with more non-cisgender individuals. We don't know if it's what we call significant differences. We know that there are some differences in the samples. And we also get the frequency tables by category of gender and also our distributions. The last thing before we move forward, if you go back to descriptive statistics frequencies and click on paste, you'll get the syntax window. Remember, we were talking about the syntax as this diary. So now we have the command of frequencies, and after you're experts in SPSS, you can just work in the syntax. You don't need the drop down windows at all. Okay, so you have age, ideology, network. Next time, if you want to include, for example, religion, and you know that it's just defined as religion in your data, you're just going to add religion, and then you're going to get religion in the output. Super easy. But for now, just be aware of this option. We don't really need syntax. Okay, let's talk about normal distribution. It's going to be very relevant later on. Normal distribution is amazing. Why is it amazing? Because if we know that we're dealing with a normal distribution, we know so much about our sample. Normal distribution, that's the mean. And we know that that's standard deviation. So let's say that we're talking about age for some reason, and the mean is 30, and standard deviation equals 10. So we know that we have roughly 68% of our sample somewhere between 20 and 40. Is it clear? Because we know that each standard deviation is 10. We know that's just incredible. We know that we have 95% of our sample somewhere between 10 and 50, right? Because now we jumped 2 standard deviations at each direction. So we can know a lot just by knowing that we're dealing with a normal distribution. Again, all the data that I have in my head right now is that I have a normal distribution, is that I have a mean. I know my mean, and I know my standard deviation. That's mu, mean. That's standard deviation. We know these numbers going back to our output. If we know that we're talking about a normal distribution or something that roughly approaches a normal distribution, look, that's just incredible. We can look at these numbers. Let's look at political ideology, for example. So political ideology, we're looking at the mean, and we see that it's 5. Oh no, that's very important. When you're working with split file, always remember to reset it, because then everything that you're going to run, every analysis is going to give you the split file. So let's just run it again without the split file. The same thing. So let's look at the political ideology scale. The mean is 4.3. The standard deviation is 1.8. So we know that we have, if we know that that's normal distribution, we have 95% of a distribution somewhere between, what is it, like 2.5 and 6, right? Slightly more than 6. And it's so easy. The only thing that I'm doing is I'm taking 2 standard deviations above the mean, 2 standard deviation below the mean. And already, mentally, I see this nice distribution. And I know that if someone said that they are 1 highly conservative, whoa, that's very unlikely. You're like in the, in the top or the most bottom percentile. The beautiful thing about distributions and samples, and that's something that we call the central limit theorem, and it's relatively easy to prove. We don't have time to prove it right now. Is that by increasing our sample, usually distributions become more normal. Think about what you call the law of large numbers. If you toss a coin, what are the odds that it's going to be tails? 51. We all know that. So I'm tossing it 1 time and it's tails. Excellent. Tossing it again, it's tails. Could happen, right? Again, tails. And I'm tossing it around 7 times. Each time it's tails. It's somewhat unlikely, but could happen. The idea of a large sample is that if you toss it enough times, it would become 50%. And again, that's the central limit theorem. We usually use 40 in a sample. Is a good rule of thumb. Everything above 30 we would recognize as normal or approaching normality. But we have to run some tests to make sure that it still works. But just remember, 30 is like a lucky number in statistics. If our sample is 38, we might be in some problem. Let's try to get another 2 people or 2 observations in our sample. So how to make sure that our distribution is normal? So having a normal distribution is very important. It has a lot of implications on the type of analysis that we can do. I don't want to go even into the complicated statistics, but there are some assumptions that normal distributions allows us to assume just by knowing that it's normal. So knowing that our distribution is normal is critical. It's very easy in SPSS. There are many ways to prove it or to show it. None of them is perfect. Some of them are better than others though. So we're going to again analyze descriptive statistics. Remember, that's the whole section is on descriptive statistics. We're trying to describe our sample, and we're going to explore now. Let's use probably age is a nice one, and use networks just because we know that it's highly skewed, right? We saw it. It's not going to be normal. Then we're going to statistics, and let's choose outliers. I want to see those outliers if we have those. And in plot, I want to ask for normality plots with tests. That's it. We can run. By the way, you can click paste, get the syntax, and also run it from the syntax. The same thing. Yeah.
How did you get rid of the male-female split?
Oh, you just go to data, split file, and reset. Oh, sorry, yeah. Get rid of the male split. Yeah. So essentially, we get most of the information that we wanted. We get some additional interesting stuff that we're going to talk about later. So there are a few things that we can do to make sure that our distribution is relatively normal. One thing is related to skewness. How skewed is our distribution? You see, for age, we have the value of skewness and its standard error. The only thing that we need to do is that we need to divide this value, the statistic of skewness, by its standard error. Regretfully, SPSS wouldn't do this for us, so we can use a calculator. And the rule of thumb is that if it's somewhere between 3.2 and minus 3.2, that's fine. If it's above 3.2 or below minus 3.2, we have a skewness problem. In this case, it's somewhat positively skewed.
Could you please explain what skew and standard error is?
Yeah. So, what standard error is?
Yeah, and skew.
In skew?
Yeah.
So, okay, excellent. Imagine this, not as a distribution of just numbers, of any numbers. That's a distribution of skewness values. So that's the average of skew. That would be a normal distribution. If something gets 3.2, it means that it's highly skewed. It's on the 99.9 percentile of skewness. You get the idea? It's if skewness numbers are normally distributed, and they are, it means that if something gets more than 3, it's highly skewed, or less than 3, or less than minus 3. Anything that falls within this distribution is okay. What it means to be skewed, it means that our distributions, if it's positively skewed, like in our case, it's like this. So for example, we have things in the real world that are positively skewed, right? Income. Many people get minimum wage Some people get very high wages and it drives the whole average up. That's skewed distribution. We don't have a normal distribution of normal distribution of wages like something out of Bernie Sanders ideology, right? We don't have that. Negative skew. Age at sorry, it's going to be morbid, but age at death is negatively skewed. Most people die at an old age. We have deaths in the crib. That drives the distribution down because babies die very young sometimes. So that's again skewed. That's not normal. Why is it important? Because we are violating some assumptions that are going to be critical later. We need to know if our distribution is skewed or not. If it's skewed, we need to do a few things to correct for it. Sometimes we can normalize it. So our rule of thumb is if we take the skew value divided by the standard deviation of the skew value. Don't want to complicate it more than I should, but what we're actually doing, we're standardizing the skew value. If it's above 3.2 or 3.29 or below minus 3.2 or 3.29, we have a skewness issue. It's not normally distributed. That's clear? Like the skew, we have the issue of kurtosis. Our distributions can look like this. Just a vertical skewness in the sense. Or distributions can be flat. We're doing the same thing, the same rule of thumb, exactly the same. We're taking the kurtosis value, dividing it by the kurtosis standard deviation. If it's higher or lower than 3.3 or lower than minus 3.3, we have some issue. And we're going to talk about how to correct for it. But we should just be aware. So skewness, kurtosis, that's one thing to assess the normality of our distribution. I said there are a few ways in SPSS. None of them is perfect. Actually, in general, there's no perfect way to assess for normality of the distribution. If you scroll down, you'll see it's called test of normality, and we have two tests. Kolmogorov, Smirnov, that's one test, and the other one is Shapiro-Wilk. These two tests are essentially ask the same question. They take a normal distribution and they ask the question, how different is your distribution from the normal distribution? If this number is smaller than 0.05, we're gonna, like, our next meeting is gonna be all about this magic number, 0.05, the significance level. If this number is smaller than 0.05, and in this case is obviously smaller, is 0.0000000 something at some point, we have a problem. It basically tells us that our distribution, both for age and for network composition, is significantly different from a normal distribution. Both according to the test of Kolmogorov-Smirnov and to the test by Shapiro and Wilk. The difference between them is, you don't really need to know this, it's a bit more nuanced. For smaller samples, Shapiro-Wilk is better because has more what we would call statistical power. But don't worry, not everything is bad, because I can tell you that these tests is what we call highly conservative tests. It's very hard to prove anything with these two tests. It's good to know that they exist, that they out there in SPSS, that you can get it in your output. You can always impress your professors with that. Very hard to prove normality. Very easy to prove enormality. So that's the second way. We talked about skewness, we talked about kurtosis, that's one thing, and now we're talking about test of normality. And finally, the best way is a QQ plot. QQ plot is different in the sense that instead of numbers, it gives us graphic. So we can observe how different it is from normality. You see this line, the straight line? It's, first of all, we call it QQ, it's quartiles. It divides the sample into few parts. And it tells us that's the line, that's how your distribution would look if we were to deal with a perfectly normal distribution. That's the straight line. Now see your distribution? That's how your distribution actually looks. So we can eyeball this and we can say, well, you know what? It's not too bad. It's not too bad. Yeah, it's somewhat skewed. We can see the problems here, right? We see that we have much more people. Remember, why is it skewed? Usually we screen people who are like 16 years or younger, right? So no wonder that we have much more people here, less people here, because at like 16, 17, 18, or I think here we screen 18 was the minimal age. We have much more people here than 80-year-old people. So that's fine. We can explain it. Remember we were talking about a variable that dealt with a network structure? And we said, well, there we're going to have a problem. We have this, what we call a long tail. Very few people know many LGBTQ individuals. Most people know one, maybe two, maybe zero. That's less relevant. We can talk about later. Look at the QQ plot for network structure. That looks bad. That's not normally distributed. Remember, the straight line is a hypothetical normal distribution for this variable. These points are the actual values. Looks bad. That's not normally distributed. But we are expecting to see something like this. Questions about normal distribution and how to find or how to observe whether it's normal or not in SPSS? 3 ways, right? Easy. So if we have problems of outliers, I didn't talk about outliers. In the descriptives, we can get extreme values. Remember, we clicked on outliers. And what it basically gives you, it gives you the 5 highest values in the distribution. No one says that these are extreme, just the highest, and the 5 lowest. And it gives you the cases. So we know that case 229, if we go back, where is it? To the data view, is this person. So they have an extreme value for age. Or, excuse me, for network composition, or somewhere. I can find it. Okay. Their age is 81. They are an outlier. And if we're concerned that somehow outliers can ruin our analysis, because a lot of the time problems with normal distribution stem from problems with outliers, we can do one of the following. We can basically remove the case. If we have enough people, we can just delete the whole case. Go back to 229. Sorry, can't use it. We can transform the data. There are different types of transformation. It's somewhat more complicated, but we can do some math on the whole variable. I'm going to give you an example of one type of transformation, which is by far the most common one. Or we can change the score. Different people have different opinions about changing the score. There's some ethical issues here. I'm changing your age, I'm like God. But what we can do is we can change the score and decide, well, I'm gonna see what's the score that's not an outlier and give you a score that's slightly higher. So if my normal distribution, remember 2 standard deviations for each direction from the mean, is 18 through 67, I'm going to give you 68, not 84. That's too extreme. You're ruining my beautiful distribution. If it's still a problem, there are some things that we can do to statistically correct for this problem. And we're going to talk about it next week. One of those is use robust methods like ANOVAs. The other one is bootstrapping. I don't know if we have time to talk about it. It's a nice cheat. It's basically what we're doing is we're extracting thousands of samples from our sample and normalizing the data. Remember I told you that the more you extract, the more observations you have, the normal it looks. So we can correct for it by bootstrapping. Okay, so let's do the transformation. The most common transformation is called, it doesn't have a catchy name now. Think about it. Basically, we want to transform it into standard units. We're going to get, we're going to analyze descriptive statistics, and this time we're going to descriptives. Let's choose age, and we're going to standardize it. Click on Save Standardized Values as Variables. Remember our beautiful normal distribution. What we just did, we plotted all our distribution of age into the normal distribution, which is 0 is going to be our new mean, 1 is going to be 1 standard deviation above the mean, 2 is going to be 2 standard deviations above the mean, 3 is going to be 3 standard deviations above the mean, minus 1 is going to be 1 standard deviation below the mean, and so forth. So now, when we look at our new variable, if we go to the end of our data set, we can see Z age. Z is for standardized values. An easy thing that we can do is basically we can sort it either by ascending or descending. It doesn't really matter right now, but we can see that our most extreme case is 2.9. So it's still here. It's fine. I wouldn't get rid of it. Let's look at this. No, we're fine. I wouldn't erase any of the cases. Did you understand what I did? It's like it's a lot to understand without having some statistical knowledge, but essentially what I did, I transformed age in years into age in standardized values. So the new average is 0, and it's from -3 to 3. Everything slightly more extreme is probably a extreme outlier. I should consider seriously consider and remove it.
Okay, so after we do this, we're just looking for values higher than 3, less than -3.
Yeah,
And if we see those values, then we might have to get rid of outliers, do something else. But because they're all
Exactly.
within the standard distribution.
exactly. Just for practice, let's do it again. Descriptive statistic descriptives, this time with network. And I told you that we're going to have some issues with this variable. You see here, let's Z network, Z descending. Look at this. Here we have some serious outliers. 5.4, it's like, where is it? If it were a distribution of, let's say, income, 5.4 is like Mark Zuckerberg, like here. Any questions about how to standardize? Standardize is very relevant for many types of calculations. For some reason we want to know where is the weather colder. Is it in London or in New York? We're measuring in New York in Fahrenheit, in London in Celsius. How can we compare Fahrenheit and Celsius? Hey, we can standardize it. Excellent. We're moving forward. Let's talk about t-tests. So everything that we did till now was in the realm of descriptive statistics, and we dealt mainly with a normal distribution. We also call it Z distribution. That's the Z in the beginning of the variable. We have a T distribution. It's very similar to Z distribution. It's a bit different. So it looks like this. However, the interesting thing about T distribution, the higher the sample, the larger the sample is, the more similar it becomes to a normal distribution. You know, just a trivia, if you ever want to impress anyone. So Z with 10 people would look like this. But you add more and more and it becomes like a normal distribution. We're working with T distribution because there are 3 types of tests that we all should be aware of. These are the t-tests, especially if you're in the comm management program. They probably want you to know these tests very well. Essentially what we're doing is we're comparing means. And the question is, in t-tests, whether there's a significant difference between means. So we have 3 t-tests. The first one is one sample t-test. We call it one sample t-test because we're comparing our sample to some criteria. It's not a different sample. So for example, I know that on average, in general, people score, like I don't remember, what do you have, GRE or SAT? GRE, and it's from 130 to 170. Yes, am I right? Did it change? Let's say that. So the average GRE score is 145. For some reason, that's what I think it is. My claim is that people are getting smarter. So today, it's higher. So I'm taking a sample of people who did recently their GRE, just got their scores, and I want to see if it's higher than whatever I said before, 145. So I'm comparing my sample to some criterion. It's not two samples, just one sample. I think that the life expectancy is higher now. We know that in the past it was 74. I think that now it's 88 or higher than 74. I'm comparing a sample of people to some criteria. Let's see how we do it in SPSS. Very easy. Analyze, okay, so we move from the realm of descriptive statistics, trying to describe our sample, to the realm of inferential statistics, trying to infer from our sample to some population. Compare means and one sample t-test. Again, I love to look at this in the variable names. It's easier for some reason. So we ask people about their attitudes toward LGBTQ individuals. So that's a scale, and that just, you get here the average of the scale. So I think the scale is from 1 to 7. Let's say that in the past, the average was 3.5. In the test value, we insert our criterion. And I want to see if the average changed, if it significantly changed. Let's say that my hypothesis is that now people are more tolerant or more accepting of LGBTQ individuals, more supportive of these individuals. So 3.5, and we moved our attitudes variable. Okay? We are running this output. Excellent. So let's just go through the output and see what we can infer. So our sample size is 243. We already knew this. That's the mean of the attitudes toward LGBT in our sample. That's the standard deviation. If we examine this and we know that it's normally distributed, you already can visualize it. You can say, oh, okay, so 95% roughly of our sample is somewhere between what? 8.5. Well, it's obviously not normally distributed because the scale is from 1 to 7. But we kind of get the idea of means as standard deviations. Here we see again our criterion. That's the t-value, very important. And what we want to see if the t-value is significant or not. How many of you know what significance means? dealing with samples. So in a sense, I don't need to run the statistics. I can just look and say, well, 5.5 is higher than 3.5. Better. Next question. But the real question is whether the things that I'm observing in the sample can be inferred to a population. What are the odds? What is the probability of observing these differences that I'm seeing in the sample in my population? We, especially in the, or I can speak to what I know in the social science, we use 95% probability of 95% or higher as a good rule of thumb. If something is probable in 95%, I can live with it. If you're in the health sciences and you're developing a treatment, you probably want to be maybe higher, maybe 99%. So that's what I'm observing here. If the significance is less than 0.05, that's the 5%, then it is significant, meaning that we have, in this case, a very high probability that the attitudes toward LGBTQ people are much better than they used to be in the past. Not an easy concept to understand, significance. Think about it. You're trying to infer something and you're asking yourself, what is the probability of observing the same differences that I see in my sample, just a sample, in the real population? So where you go, like you finish with school, go work in the industry, and they want you to see if the product is outselling a different product or the competing product. Then they don't want you to tell them, well, that's what I found in my sample. Who cares about your sample? They want to know what happens in the population. That's where you start talking about significance. It's significantly, there's a significant correlation. Nice. Now I know that the things that I observed in my sample can be inferred to my population. Yes?
So I'm just wondering what the number for the value for the T means.
The T is the T statistics. Essentially what it means, there's a distribution, like we said, there's a T distribution. Where is it? It's a number on this distribution. I can tell you, and you can check it later, that by the way that the T distribution looks, to get a 19, a T of 19, it's very extreme. And that's just because these differences are huge. Look, we moved from 3.5 to 5.5. That's incredible. We moved 2 points on the scale. I just made up this 3.5, right? I don't know what the real value was. So the T is associated with the t-test. We want it to be as high as possible to prove that there is a significant difference. But mainly what we're looking for is the significance here. That's the mean difference. That's basically the new mean minus the old one. And we also get a confidence interval. Confidence interval, without making it more complicated than it should be, it's another way of looking at significance, another way of thinking about significance. So I can tell you that, you know, before the elections, people were saying that there's a 99 chance or probability that Hillary is going to be the next president. That's like significance. We're talking about probabilities. Confidence interval is if I told you that Hillary will get somewhere between 48% of the popular vote to 53% of the popular vote. You see? So it's the difference between the probability that something would happen and the interval within it would happen. So essentially, if we're going back to our example, we have a very, 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 very high probability to observe the same differences in the population. But we need to remember that that's the difference between our sample and this criterion. However, in the population, the difference is going to move somewhere between a lower limit of 0.8 and a higher limit of 2.2.
Correct me if I'm wrong, but as far as I know, I think there was like a number for the significance that whenever conducting like social science related research, the number that serves as a stamp, like criteria for if you have this number for significance, your research is your data is actually
0.05,
significant.
yeah.
That's 0.05.
Yeah, it's 0.05.
Okay. So it should be less than 0.05?
It should be less than
Like
0.05.
less the better.
The less the better. Because if it's less, then we're saying 0.05 basically 5% of being wrong.
Oh.
It's 95% of being right.
Okay.
And it's not a perfect number. It's somewhat arbitrary. It's funny because there's some studies that plot all the significance that we report in journals, right? So you see that the distribution is like 0.5 and then it drops down. What does it mean? It means there's some shady business going on because it's supposed to be normal. But if it drops down after 0.5, it means that people are doing something to get to 5 because they know that that's the criterion that's going to get their, results that they want to get. Okay, so moving on, that was the first t-test. Now we're going to talk about the second one. By the way, we don't see a lot of one sample t-test in the literature. We don't use it a lot. It's not that common. The much more common test is the independent sample t-test, which is the basic thing that we use when we do, for example, an experiment. We have two samples, and we're comparing the means between those samples. And we want to see if there's some significant difference between the means. What's very important to understand about the two-sample t-test or the independent sample t-test, the assumption here is that we're talking about completely different groups, two different groups. There's no chance that the same person can be in the two groups at the same time. Males versus females, group A versus group B. If I have the same person in both groups, it just ruins all the assumptions of independence that sample t-test, that the two-sample t-test uses. So I told you that we had two conditions. One condition was terror attack frame, the other condition was the hate crime frame. So let's just run this, basically the basic assumption of this paper. So we're going again to compare means, this time independent samples t-tests. Now we need to choose what's going to be our grouping variable. Our grouping variable is called condition. And if you go back to the data set, you can see how we defined it. And in terms of values, you can click on values and see what are the values. I just happen to remember that 1 and 0 are the two groups that we're comparing. 1, I think it's hate crime, 0 is terror attack. There's no way that the same respondent can find himself or herself in both conditions, because they were randomly assigned to different conditions. And our dependent variable in this case, what are we actually measuring, what difference do we want to see, is going to be again the same thing. Let's look at attitudes. And let's also look at policy. Policy is a scale of different policies that would benefit LGBTQ individuals and how much people support these policies. And our assumption again, if you're exposed to the hate crime frame, you'll be more supportive, because you tend to see them as a victim in this specific incident. Okay, let's just run. We don't need to change anything else. Okay, nice. Now we have slightly more info here, because we have 2 samples, not 1 sample. So in terms of attitudes, we see that we had 122 people in the hate crime frame, 121 in the terror attack frame. In terms of means, we see a slightly higher mean in the hate crime frame. Yay! That's what we wanted to see. And we get also the standard deviation. So people, after exposure to a news article that framed the event as a hate crime, tended to have more supportive attitudes towards the LGBTQ community. Let's see if it's also true of the policy. It is. Slightly more. Not a huge difference again, but slightly more. That's the descriptive information. I'm describing the samples. Who cares about it? Really no one, because I want to know whether the difference is significant. I don't care about the sample. I use people from Qualtrics. I paid the money. I'm not sure that I know that it was quite representative, because that's what we asked for. That's what we probably got in terms of distribution of variables. But I want to know what happens in the population. Before I'm talking about, I'll go to talk about t-test. There's one tiny thing that we need to do, only with the independent sample t-test. We call it Levine's test of equality. We need to ask ourselves a question, whether the variance, remember, we talk about variance, one of the measures of dispersion, whether the variance in the conditions is equal or not. Because if it's not equal, we need to do something slightly different. It's very easy in terms of SPSS, I'll show you. But if it's not equal, then we need to tell SPSS, well, hey, check this. Don't do your usual thing. It's not equal. So we're looking at the significance of the F test, which is associated with the Levine's equality test. If it's non-significant, remember, if it's less than 0.05, it's significant. If it's higher, then it's not. So it's not significant in both cases. It just means that we can be sure that the variance is equal. So we're just going to read from the top line. However, if this number was less than 0.05, we were to read from this line. Now that's not a huge difference, it's almost the same, or the same number. Not a big deal, just so you know. Sometimes it can be slightly different. And here we have the same thing. It's not significant, we're reading from the first line. It is significant, we're reading from the second line. So let's see the results for our independent samples t-test for attitudes towards LGBT. That's the t-value. Nice. It's not as high as we had it before, but it is significant. It's less than 0.05, 0.036. Nice. Okay, so we supported our hypothesis. There was a significant difference. Participants who were exposed to the hate crime frame tended to report on better or more favorable attitudes towards LGBTQ individuals compared to participants in the terror attack frame. Is it also true for the policy? No, it's not significant. Even though there is a difference between the means, and we also see the same difference here, it's not significant. Another way, because I told you that significance and confidence intervals go together, that's two ways of answering the same question, essentially. We can also look at the confidence intervals. And the interesting thing here, if somewhere between the lower limit and the upper limit, there's a 0 in this range, it's not going to be non-significant. And I'll tell you why in a second. So here we don't have a 0, but here we do, because if our lower limit is minus 0.19 and our upper limit is 0.61, we have a 0 in this range. Why is it non-significant? So even if I didn't have this, I could have told you that it's not going to be significant. Remember our example with Hillary Clinton and how much percent of the popular vote she's going to get? Here we're basically telling you that there's a difference in the population, in the sample, sorry. But in the population, the difference can be either less or more. I don't know, the difference, you can have more support in the hate crime condition or more support in the terror attack. I don't know. It goes from minus, the difference goes from minus to plus. Is this thing clear? So when we're analyzing confidence intervals, we essentially really are praying that in this interval we won't have a 0. So if it's all positive, excellent. If it's all negative, excellent. Because our hypothesis can be sometimes, people had less stigma before, that would be negative. Less. We just don't want to get the 0 in the interval. Last thing for today, the last t-test, very simple one, is called the paired samples t-test. That's all we have, 3 types of t-tests. So we had the first one, which was one sample t-test. We compared our sample to some criteria, some external criterion, coming from a sample. We had 2 independent samples that by definition, I told you that there's no way that the same person can be at the 2 groups at the same time. Paired groups, we're talking about two related samples. So it can be people before diet, after diet, the same person. It can be married couples. By definition, these people are related. It can be the same person before intervention, after intervention. That's a paired sample t-test. Why is it different? Why is it relevant? Just, think about it, that if we're talking about the same person and not different people, they are probably more similar. Right? That's you before the intervention and you after the intervention. That's different than comparing between two different people. So you need to tell it to SPSS, because SPSS need to be slightly more conservative. Right? If we're talking about the same people, it's in a sense easier to detect differences, because you're the same on all the other variables. Nothing changes. So we are at a risk of running what we would call a liberal test when we should run a conservative test. So always ask yourself the question, are these the same people? Are they somehow related? Maybe these are twins. We want to ask a question about twins. We need to run a paired sample t-test. Analysis, compare means, paired sample t-test. And one of the things that we measured here, we measured in-group identification is how the extent to what people are proud to be American. So identification pre is before the intervention. Identification post is after our intervention. The same people. And we expected that to see a reduction, especially in the hate crime condition. Are you with me? Okay, let's run it. Nice. Whoa. Whoa, that's huge. Okay. Again, the first table just tells me the descriptive statistics. What happens in the sample? Means, number of participants, standard deviations. Nice. This table, for now, we ignore it. We're going to talk about correlations next week. Paired sample t-test, that's what we need to know. Look at this. That's our t. That's our significance. There's a significant difference. Before, on a scale from 1 to 7, people reported on being 5.8. Now, after the intervention, they're 2.8. And this reduction, this decrease in, patriotic sentiment, or whatever you like to call it, in group identification is significant. And remember that we can also gauge the significance from the confidence interval, because we see that we don't have a 0 in this interval, right? From essentially what we're saying is that we're saying in our sample, the difference from before to after is 3.01. In the population, the difference is going to move somewhere between 2.79 and 3.23. It's still going to be significant. It's still going to go down. I just don't know how much. Any questions? Next week, we're going to talk about correlations. We're going to talk about ANOVAs. We're going to talk about regressions. And we're going to talk maybe about scale construction if we'll have time. And I don't know if you're doing your projects right now, but if you have questions, first of all, don't hesitate to email. I'll try to share the slides with you. my email is there. And definitely bring your questions here, okay? It should be also maybe more workshoppy, so you can raise questions or problems or issues that you have. Thank you so much. Let me know if you have questions, and if you have my USB drives. Thank you, Nancy. Also, in terms of feedback, if you have anything that wasn't clear, you want me to talk about it some more next week.
When did you do that?
From ICA, I was on a flight with TJ.
Okay.
And I don't know if you remember, but the attack happened when we were in Japan.
Yeah, yeah.
And we started talking about what can we measure, and the design was
That's pretty cool.
yeah,